Good afternoon, ladies and gentlemen. My name is Si-Hoon Lee. I'm one of the moderators this BrainLink X-Lab Day talk concert. The X-Lab Day talk concert start right now. So today's topic is research and policy trend on the production and hydrogen and production and utilization of clean hydrogen and ammonia. So it's our first day. We just see the small video. Yeah, let's play the video.
Amidst the world's rapidly accelerating changes and competition, what kind of future are you preparing for? We are chartering a path to the future through science and technology exchanges, bolstered by international cooperation. In this era, where scientific and technological competitiveness is directly linked to a nation's diplomacy and security, the power to overcome such challenges lies in international cooperation that fosters synergy through collective efforts, and from talents who will shape the forthcoming era. The scholars of the world are gathering in Korea. A platform that facilitates exchanges between Korean and international scholars, as well as between seasoned and emerging researchers, is taking shape. BrainLink X-Lab Day, organized by the Korean Federation of Science and Technology Societies, aims to be a global hub of talent. By consistently enhancing and expanding the global talent network, we're laying the groundwork for a brighter future. By inviting global scholars, X-Lab Day provides an opportunity for young Korean researchers to glean insights from the vast knowledge and experience of both Korean and international scholars, as well as to engage in collaborative research. In 2022, the inaugural X-Lab Day saw a total of 14 meetings across various technical fields. Altogether, 449 individuals participated, comprising 70 from overseas and 379 from Korea, all aiming to build a stronger network in Korea and abroad. This year, for our 2023 X-Lab Day, we have the honor of having Xingteng Yao, professor at Tsinghua University and a Fields Medal winner, Philip Kim, a globally renowned professor at Harvard University, known for his research in graphene, Yun-Sung Hwang, professor at Stanford University and Hoam Award winner, and Humboldt Research Award winner, Zhigang Suo, professor at Harvard University, leading discourses of their respected fields. This year, the discussions will span 12 national strategic technology fields pivotal to Korea's advancement, including quantum mechanics, nuclear technology, and AI. The event will see the participation of 30 Korean and international scientists and engineers. With 2 organizers leading each technical segment, the gathering will foster in-depth academic exchanges, encompassing the sharing of recent trends and information in core technology fields, in-depth discussions on research findings, and the sharing of ideas. The focus of X-Lab Day is connectivity and sustainability. Following the event, communities and clubs will be established based on each X-Lab Day session to ensure ongoing dialogue among attendees and promote collaborative research. To ensure that today's dialogue becomes the seed for tomorrow's magnificent achievements in scientific and technological development, COAST supports the reinforcement and expansion of the networks established through X-Lab Day. COAST, the organizer of X-Lab Day, stands as a beacon for Korea's science and technology society. Established in 1966, its mission has been to safeguard and amplify the rights and interests of scientists and engineers. Our endeavors extend to enhancing the public's grasp of science and technology and furthering its development through comprehensive policy research, planning, surveys, and consultations. As Korea's largest science and technology network, with over 600 affiliated organizations, we are committed to promoting domestic and international cooperation and exchange. In the transformative era of the Fourth Industrial Revolution, where science and technology spearhead groundbreaking challenges, KOST remains dedicated to its role as a facilitator of scientific and technological innovations. In this era of technological dominance, we will navigate through the fierce competition by fostering global cooperation in the fields of science and technology. BrainLink XLab Day aims to broaden both domestic and international talent networks and become a global hub of talent. By making XLab Day into an event that scientists and engineers worldwide eagerly join, we intend to elevate Korea's global standing and bolster national competitiveness. Global Talent Hub, BrainLink XLab Day.
I'm very nervous because it's the first time to be recorded. So anyway, today the talk consists separated into two parts. The first part is some short presentation of the foreign scientists, and second part is some of the discussion. So please welcome the first presenter, the Professor Choi. So Soryong Choi, Professor Choi is the professor at the University of Cincinnati, and his topic is global strategy for the production and storage of ammonia. He'll talk about the status and there's some challenges and opportunities for sustainable future. Please welcome Professor Choi.
All right, thank you so much, Professor Lee. First, before starting my talk, I want to thank you, moderators, Professor Lee and Jin. I appreciate your tremendous effort to have people here having this nice opportunity. Also, I want to thank to the Mr. Park and his staff of the International Cooperation Division at KOF-IST. So I really thank you for your effort and support and kindness having these people here. So I really appreciate for that. So with that, let me start. So hopefully you know this figure how our Earth, Mother Planet, getting warm and warm. So we believe this temperature goes up because of human activities. Now we are looking for maybe we have about 2.0 Fahrenheit or 1.5 degrees Celsius increase, and it creates a lot of climate changes. So we are trying to reduce or mitigate this temperature increase by thinking, shifting our energy sources and many different infrastructure to mitigate these changes. But this is a very important step for us, thinking about what can be the energy carrier, not a coal-based one, not petroleum-based energy resources. What will be the best candidate to mitigate the climate change? So one of the best candidates, I would say, will be hydrogen. So if you see here, hydrogen, there are a few different types of or colors of hydrogen. We are talking nowadays. Gray hydrogen is pretty traditional, hydrogen we can produce from natural gas, but it produces a lot of carbon dioxide. But now we are shifting to blue or green hydrogen, which incorporate the carbon capture. Also, we have energy hydrogen generation from renewable energy sources. So that will be our future. So why hydrogen is so important? Because if we think about their volume and the energy density, this is pretty much obvious. When we drive a vehicle to get the 500 kilometer range, you may need a 10-gallon diesel. But if we have a lithium-ion battery, the volume or the mass of lithium-ion battery is tremendous, maybe more than 10 times. But hydrogen is very competitive, so we just need a 6 kilogram hydrogen to fuel the car to have a 500-kilometer range. So this is an obvious benefit why we are looking for hydrogen as an energy carrier. However, still hydrogen should be produced in a sustainable way, so we can reduce the carbon footprint. Then we can achieve a very sustainable society. So on the graph, very last one, if we have hydrogen from renewable energy sources, the carbon footprint very, very low, maybe close to 10 grams CO2 per kilowatt hour energy. So this is maybe our target for our future. And how we can store hydrogen, there are some other ways, but typically we use a physical method. We can compress, we can change gas to liquid, and also we use some material including adsorbent, MOF, or some hydride forms. So we can store hydrogen and we can release them whenever we need. However, if you see this graph, there are so many operating conditions to limit the practical storage of hydrogen. For example, on the left, if we looking for liquid hydrogen, pressure will be very moderate, but temperature minus 250 degrees Celsius. If we see the compressed hydrogen form, temperature about room temperature, but we need a very high pressure. So there are some pros and cons for each method about carefully thinking the operating condition, how we can compress or how we can store it, how we can release hydrogen. There's a practical approach is how we make this approach more economically feasible. So please remember that, not just hydrogen, but there are a lot of energies involved to capture or storage hydrogen and release for energy production. As one alternative, I'd like to talk about ammonia. Ammonia has very high volume hydrogen density, about 120 kilogram hydrogen per cubic meter. And ammonia, it has very high auto-ignition temperature and low condensation pressure, and also lower gas density than air. So there are many benefits. We can use ammonia as an energy carrier, then can be a source for the hydrogen production. So on this graph, on the top, I'm sorry for the small character, but ammonia indicating very high gravimetric hydrogen density, and also blue bar indicating volumetric hydrogen density. So it will be a good candidate as an energy carrier. How we can produce ammonia? If you are working in the chemical engineering area, traditional Haber-Bosch process is very famous. We first produce a syngas containing carbon and nitrogen, hydrogen. Then that goes to the reactor at very high temperature and pressure. Then eventually we produce N2H2. Then through the condensation, we can produce ammonia. And also there are other methods based on electrolysis. So we produce hydrogen through the electrolysis, and also we got a nitrogen from cryogenic distillation, then followed by the traditional Haber-Bosch process, we can get the ammonia. And also people studying the electrochemical synthesis. So we have a cell having anode and cathode. So we produce H2N2. Then there is a cathode reaction, another reaction, then we can produce ammonia. However, if I highlight what is the challenging point here, we need to separate ammonia, and also we need to separate hydrogen and nitrogen to recycle them into the system to increase the efficiency. So there's a very good R&D point for the future. And while I'm talking about ammonia and hydrogen separation, because they are very close to each other. So ammonia 2.6 angstrom, hydrogen 2.9 angstrom. Technically, it's very hard to separate them, but scientists are working hard. They invented a very nice material, having very sharp cutoff, so they can separate ammonia, hydrogen very efficiently. And the last method I want to introduce, this is maybe the second last one, thermochemical cycle. So if you see here, we have a carbon source, and we have a carbon precursor. Then when we have aluminum oxide, we can have aluminum nitrogen. Then we oxidize the aluminum nitrogen to ammonia, so we can get ammonia. So there are a lot of thermodynamics involved here for the reduction in steam hydrolysis. So there is a good challenging for our society. Lastly, also we can convert NOx, which is nitrite to nitrate to ammonia. So there is one very nice study using plasma. They first formed the nitrite to nitrate in water, and they use that nitrate to produce ammonia. So this is a very early stage study, but still I believe there are a lot of good things happening in this area. Once we have ammonia produced, the next step, we transport that ammonia and we get the hydrogen. But I'm sorry for the small character, but through the electrochemical reaction, thermochemical reaction, photocatalysis, and plasma catalysis, if you see here, we can get the hydrogen from ammonia, but a lot of catalysts involved and also thermodynamic involved. I'm sorry for the small character, but I would highlight all this methodology or technical point feasible, but still we are suffered from high operation cost, and also the instability of the material, and also some stabilization of this process. So there are still a lot of things that we can work together to make green ammonia. So with that, I'd like to conclude my talk saying ammonia, which is a very potential or good source for hydrogen carrier, but we need the ammonia production and decomposition. So at the moment, lithium-based catalyst, which is a winner in the market, but whether we can find the more economically feasible material, stable for long time operation, that's a challenging point. To separate hydrogen from the mixed gas, metal membrane is quite promising. There are a lot of studies, but still it's a very expensive material. So maybe whether we can fabricate some hybrid type membrane to have a better efficiency, selectivity to separate hydrogen, that is a challenging also opportunity for us. With that, through this BrainLink X-Day, I met a lot of good fellows and experts working in this area. So I'd like to launch a special issue on this topic through this nice discussion. So that will be some special issue next year in the Chemical Engineering Journal. Then I'd like to see that happening through these wonderful opportunities. So with that, thank you so much for your kind attention.
Yeah. I know you have a question, but the question will be the answer in the second time, the discussion time. So I introduced the second lecture, the Professor Shou. Yeah, please welcome the Professor Shou. Professor Shou is the professor in the California University, and his topic is the miracle between the microalgae and hydrogen and ammonia.
All right, thank you so much, the chairperson. Right, this is my first slide. My first slide always start with thank you. I would like to thank the BrainLink X-Day for inviting me all the way from Abu Dhabi to here. My name is Shou Paulok, and call me Paulok. I'm from California University, Abu Dhabi. At the same time, I'm also affiliate with UNISA Nottingham, Malaysia. Right, so let me kickstart with the first one. So today's topic will be the miracle between microalgae and hydrogen as well as ammonium. Right, so please allow me to give you a quick introduction about microalgae. Right, why microalgae at the beginning? Right, so to let you know that microalgae actually is a photosynthetic plant which can grow very rapidly, can grow very fast. Yeah, within 24 hours, 36 hours. Right, so microalgae also with the growth of carbon dioxide, sunlight as well as nutrient-rich water. Nutrient-rich water can be salt water, can be seawater as well, can be wastewater as well. So the ranging of the microalgae can be unicellular, which is single cell, to the multiple cells, which is a lot of cells, with the size of 0.5 micrometer, which is very small, molecular, as well as can be very big one, as well, we call it seaweed, can be up to 100 meters. Right. Just to let you know that there is a lot of composition ingredient inside this microalgae. So the first one will be the carbohydrate, which you can use to make bioethanol, biobutane, bioplastic. While the second ingredient inside this microalgae is a protein, which you can make animal feed, human nutrient, single cells, as well as cosmetic and biofertilizer. While the last but not least, the special ingredient inside this microalgae, which everyone want to get it, which is lipid, which is oil content in microalgae, which you can use it as a biofuel, as well as with other nutrient products. Right? Of course, we cannot forget there is another variable compound inside this microalgae. Example, vitamin, mineral, pigment, carbohydrate, which is you can use as a supplement, use as a cosmetic product. Right. Just to share with you a little quick fact about microalgae. Microalgae actually is superior to conventional protein feed. Why we say so? Because you can see in order to produce microalgae, right? This is the one. Okay, to produce 100,000 kg of protein, you only require 0.5 to 2.5 hectare of land, which is really relatively less land compared to the crop that you want to produce that much of protein. So this is very good for future food because nowadays the more and more population coming in, so we have limited land for our human beings. So that's why we need more food. That's why we need more land to grow enough protein for our human being. Right. So how about lipid? Lipid we're able to grow biodiesel, biofuel, right? So you can compare with the soybean, sunflower, palm oil, right? Microalgae actually have relative strong in this point, which is biomass oil, which is very strong in terms of oil yield, in terms of land required, in terms of biodiesel productions. So you can see it's very strong compared to other crops. Right, so please allow me to give you a quick flavor about this microalgae as a sustainable future food source. Yeah? So you can see a quick graph from here, right? So spirulina powder actually is microalgae. So you can see we consist of 65% of protein in the protein content compared to the beef, compared to fish and the eggs that you eat every day. That's why you can see a lot of aerospace people, NASA, they do not bring meat, chicken to the space. They only bring some spirulina powder. This is enough for them to sustain in the space. Okay, so this is another thing. So what is the application of this microalgae? Okay, let me list out few of its applications. Right, the first one is you can produce hydrogens, yeah, biohydrogens. Second is bioelectricity. This is sustainable building. So with this sustainable building, you can produce electricity to power the electricity in the buildings. And bioethanol, right? Biogas, biofertilizer, biocrude, pharmaceutical product, which is a DHA, EPA, biocompound. Future food, yeah, because now it's a very hot topic, plant-based meat. That's why you can use microalgae to grow future food. What microalgae also have the ability to absorb heavy metal. That's why you can see we can use as water cleaner in the industry. As well as pigment, as I mentioned, azacitidine, fucosidine, all this is an ingredient pigment available in this microalgae. And last but not least, microalgae is a third generation biofuel. That's why you can use as a biodiesel. Right, so let me share with you what is the relationship between the microalgae and hydrogen and ammonium, right? So let me show you a little idea of the ideal microalgae. So in ideally microalgae, actually we always aim to get a high yield of light intensity, robustness of the stable, resistant to infection, insensitive to the high oxygen concentration, large cell with the thinner membrane. All this actually is very important because this is the idea, the best microalgae that we look for, right? So we always do a lot of isolation to look for the best strength, best microalgae in the field, right? So in order to look for the best one, right, so we need to get as much as the ingredient that we want. So you can see this is the carbon dioxide from the industry. So we can produce microalgae liquid. For microalgae, we can extract it to become microalgae powder. So at the same time, we can undergo this hydrothermal biochar, then you produce nanopore biochar. So of course, microalgae also have a ammonia removal in the system here. Right. So let me share with you another fact relationship with ammonia here. This is you can see ammonium nitrogen wastewater, right? You can produce nitrogens as well as to produce microalgae. Then we have produced photosynthesis bacteria. So this all you can see there's produced biodiesel food as well as protein food. So and for information also now carbon capture become a very hot topic. So microalgae play a very important role. So microalgae can use as a carbon capture, then ammonia used as a carbon replacement. So from all the overview, right, you can see actually microalgae production actually produce bioammonia. So impact of the microalgae growth, which is ammonium in the aquatic system, as well as ammonia removal using microalgae purification system. So actually there is a relationship between everything. So just to let you know, there is some relationship miracle happen in between microalgae and ammonium. Right. So let me proceed. How about the hydrogens? Right. I think this is very common in terms of hydrogens because microalgae is very famous in produced biohydrogens. So you can see the latest publication starting from 2001 2013 until 2022. So you can see we keep a lot of publications. From microalgae biomass, you can go a state-of-the-art, which is the nanoparticular biophotoreactor, genetic nanopolitics, and as well as a microbial fuel cell. You can produce a lot of biohydrogen. From the biohydrogen, you can have a lot of applications. Can be used as a metal production, power generations, fertilizer industry, chemical industry, oil refinery, synthetic and transportation. Right, so let me share with you a little bit of this relationship between it. So, at general, right, you can see it is required circular algae biorefinery. So, from the algae growth facility, you can produce as much biomass in terms of microalgae. They undergo a thermal, hydrothermal liquefaction, which is we call HTL. Then you will produce a lot of this ammonium. From the ammonium, they recycle again using this circular algae biorefinery. Right, so what is so important, right? Because nowadays, I believe in the past, we are talking about first generation of biofuel. So everyone talking about corn, kawas, and also the sugar cane. So second generation of biofuel, we're talking about lignocellulose, right? Lignocellulose, which is bio-waste, sugar cane, palm waste. Then third generation of biofuel, actually, everyone talking about microalgae. Right, that's why you can see microalgae produce a lot of biodiesel, biofuel, right? But this is history become. Nowadays, I believe the fourth generation, starting from 2022, everyone talking about fourth generation biofuel, which is we need to look at AI, artificial intelligence, with the synthetic biology, which is we modify some genetic modification inside so that we can produce as much production that we want. Right, so let me share with you the new artificial intelligence in X-ray technology, which is already patented. The name is called Biophysics Submission Bioseparation System, right? So this is how we develop it, and currently we have a demo plant in our lab, so whenever industry comes, they can have a demo plant of it. Right, so let me share with you this X-ray technology. Actually, we are just very simple. We just extract microalgae using our system. This is we control using temperature sensor, ultrasound sensor, pH sensor. Then we link to the Arduino motherboard. Then we link to the Wi-Fi to have a big data analysis under cloud system. Then connect to the digital technology, which is a mobile phone, your computer. Then this is the interface that we have developed with the apps that we developed. We can see the water level, temperature, real-time monitoring, as well as pump control. Right, so let me continue with the smart X-ray technology. Right, so this is smart technology that we generate. I think this is a short video. Yes. Right, so this is a short video to share with you how the smart X-ray technology works. Basically, it's undergo a cultivation process. We take around 7 to 14 days after cultivation process. You can see a two-layer happen. Right, the top layer basically actually is a biomass undergo a certain process we call temperature heating process, which is around 40 to 50 degrees Celsius. You can see the top layer actually consists of oil, and bottom layer actually consists of the biomass, which you can recycle. So of course, we claim it as smart because we have the digital as well as sensor in the between, so we can monitor and control it and feedback it at the same time. So this is we call it smart technology. Actually, this is a new pattern that we have got it, and some industry using it not only in microalgae technology, in the wastewater, in the as well as the food waste industry as well, because we can use this extract the active compound that we want. Right. So, this is almost my last slide. So, just to share with you, actually we have in the process of develop the largest biolignite integrated farm in Malaysia. This is an industry project together with government project. It's considered one of the largest spirulina microalgae farm in Malaysia. The main product actually is produced spirulina, which is for pharmaceutical products. Then at the same time, any residues, we will use it in the food and animal feed. Of course, yeah, we can use it as a color pigment because Malaysia very famous on batik, which is a cloth batik. So we extract the active compound from this pigment to use in the dye industry. Right, so just to share with you, this is our book. Starting from 2019, we all have a mission to have some books, which is the first book that we produce, we call Bioprocess Engineering. Second book, we call Liquid Biophysics System, which is extraction technology that we are doing. Then third book is Industry 5.0, right? So because during the pandemic, everyone was talking about 4.0. So what happened 5.0? So that's why we come up with the books. Continue with microalgae, which is one of our expertise. We produce a book under CRC's press. Then this is a new book that we produced this year. So we talk about the multi-phase, because we are not only two-phase, multi-phase. And this is the latest book we produce next year, starting from next year, especially invitation from Elsevier. This is a handbook in very comprehensive textbook related to algae sustainability. Right, so it's a 6-year project. Right, so just a bring home message, right? So if you want to walk fast, please walk alone. But if you want to walk far, walk together. This is something I created from one of the very famous entrepreneurs. So I believe this is a good opportunity, this is a good platform for us to work together. So we hope that we can work together, go for farther. All right. So thanks from Prof. Lee, for inviting me here and the organizer. Right, this is my team. Thank you so much.
Thank you. Thank you. Please sit here. Yeah. The next speaker is Dr. An. He is a senior researcher in the University of Edinburgh, and his topic is a breakthrough in absorption process technology for CO2 capture through PSA SPUL, along with the insight from a process engineer on assessing CO2 selective absorbent. Yeah.
Thank you very much. First of all, I would like to thank the two moderators and COPS for organizing this fantastic event, and it's my honor to have a chance for me to give a talk in this BrainLink X Day Lab talk concert. So my talk is on the adsorption process technology for CO2 capture. So adsorption is the one of the gas separation processes for CO2 capture. So we developed a new capture technology named the PSA SPUR recently. So I would like to introduce this process to you. And actually nowadays we sense the climate change taking place, and then the Korea and the UK have a same or common policy and goal for decarbonization to tackle this climate change problem, and which is to achieve net zero emission by 2050. And there are many different ways to achieve this net zero emission by 2050, including renewable energy like solar, wind power, or nuclear power, but also hydrogen, the clean hydrogen, and the carbon capture and storage have been identified one of the ways to achieve net zero emission. So there are several carbon capture processes have been, that have been commercialized already in the UK and Canada, in the US, Canada, sorry, and this is one of the example. So there are many carbon capture technology at the moment being developed, but the most conventional technology for the carbon capture is the amine process. Amine process is the gas absorption process using monoethanol amine solvent. And this monoethanol amine solvent is circulating between the absorber and stripper. And in the absorber, the CO2 is selectively captured, absorbed by the amine solvent. And then this amine solvent is sent to the stripper, where the solvent is regenerated to produce high purity of CO2. And also in the absorber, there is a countercurrent contact between the flue gas and the solvent, so that the capture reaction taking place. And as you can see, the photo on the right in the slide shows the actual commercial plant of the amine process that has been commercialized for the decarbonization of the coal-fired power plant. So as you can see, the big tower here shows is the absorber, and the size of the absorber is massive. So compared to other unit in the power plant, the tower for the absorber is big. So as you can see, the capital cost for the amine process is very high. Also, the energy consumption required for operation of this process is very high. The energy consumption is around 3.5 megajoule per kilogram CO2 captured. So once you capture 90% of CO2 from coal-fired power station, the actual amount of the electricity generation will be reduced by 1/3. So for that reason, the power plant operator are very reluctant to implement this carbon capture process. And also for the hydrogen, the carbon capture process has been commercialized to decarbonize the hydrogen plant. So by doing that, we can produce blue hydrogen. And in that case, they use adsorption rather than absorption. So adsorption is also one of the gas separation process to capture CO2 using solid solvent. And this is the Professor Che commented. This is the gray hydrogen process to produce the hydrogen from the natural gas. The natural gas is reformed to the synthesis gas, and then synthesis gas is sent to the hydrogen purification pressure swing adsorption to purify the hydrogen. And in that case, the air products use the vacuum pressure swing adsorption to capture CO2 from the high pressure sink gas. And then that the CO2 depleted gas is sent back to the SMR hydrogen plant to produce hydrogen. And as you can see, on the photo on the right, the red circle indicate the CO2 capture process. The size of the column is much smaller than the amine absorber. So in that sense, the capital cost is low. Also, the energy consumption of the adsorption process is estimated almost half of the absorption amine process. And this is the data from the CEPA about the CO2 emission from the power and industrial plants in Scotland. And the first one is the power plant using the natural gas. Obviously, the power plant emit lots of CO2, more than 1 million tons per year, but the others plant emit less than 1 million tons per year. And then the plant highlighted in the yellow is relating to the oil and gas chemicals plant, and the others are cement and the whiskey plant, because Scotland is very popular, famous for the whiskey production. So I think the first one for the gas combustion power plant, probably amine process must be the best. But for the other plants, I think the adsorption process more suitable for the decarbonization. And we developed a PSA spur technology to decarbonize this, the small to medium scale of the emitters. And this is based on the pressure swing adsorption. And we filed the patent application this year. And we entered into the NDA with external organization for technical evaluation. And also we started the new project funded by the UK EPSRC. And we are collaborating with the HD KSOE, the largest shipbuilder in Korea. And we are comparing our PSA spur process in comparison to the amine process. Basically, our PSA spur process spends less energy than the conventional amine process. Also, our PSA spur process can spend less energy by implementing temperature swing as well as pressure swing. So we are demonstrating this process in the lab. So this is the PSA rig we are using for the demonstration of our PSA spur process. The adsorption column are inside the oven. We are using the Zeolite 13X as a solvent, which is the CO2 selective material. And we achieved the very high CO2 purity and recovery from the demonstration. And this is summary of the experimental result. So we are targeting the decarbonizing the ships by capturing CO2 from the flue gas from the ship engine. So the flue gas contains 6.4% CO2, and then we send this flue gas to the PSA spur process. We can capture CO2 then we can produce 95% purity CO2 product. And the productivity is very high. We are using commercial solvent. There's no temperature swing, and we don't need very low disruption pressure. So I'd like to thank various funders to support our research. And obviously, also, thank you very much for your attention.
Thank you, Dr. An. So now I introduce Dr. Xinyan Wang. He's a senior researcher in the Brunel University. So his topic is hydrogen combustion engines for net zero transport and power generation. Yeah.
First, thank you very much for the introduction. I'd like to thank the organizer, Professor Lee, Professor Jing, as well as the host, KOFST, for inviting me to attend this event. So today I'm going to talk about hydrogen combustion engine. And obviously today I will initially give a background on why we are working on combustion engine, and also I will share some our recent results. Obviously, we have a challenge to reduce global temperature. You can see the temperature rise in recent 20 or 30 years, significant increase. And we believe there's a close correlation between the carbon emission and the global temperature. You can see the significant increase of the carbon emission in recent 50 years. And in the UK, the government has already published the target. By 2050, we should achieve net zero. But it's not easy because it's very difficult to decarbonize, in particular for transport sector. You can see in the UK, about 27% of the carbon emission are produced by transport. And you may want to use EV to decarbonize, but actually in the UK, currently, there's still around 83% of the vehicle, the new vehicle, they're still using a combustion engine and they are burning fossil fuel. And for these heavier vehicles, for example, aviation, the agricultural machine, marine, and these off-road machine, they would rely on very powerful propulsion system, which need a lot of power density. And these are quite difficult to be decarbonized by using battery electric system. For example, this is a ship. Obviously, this is a long-distance ship. It will travel around 10K mile. And if we use battery, if you look at the bottle, you will see that for the whole capacity, you have to really to have the battery itself, and it couldn't have goods on the marine, on the ship. So obviously, it's very difficult to use a battery for these long-distance marine. So if I summarize these challenges, you'll be able to see for light-duty vehicles, we can use battery or we can use fuel cell to decarbonize, but still need time to increase the market share. And for the heavier vehicle, it will be very difficult to use the EV. Then we need to develop technologies to decarbonize these sectors. So we propose we are going to use hydrogen or hydrogen-based fuel and the electric system, and also optimize the engine to achieve this goal and for these heavier vehicles. Why we use hydrogen? Obviously, it is a good energy carrier. So you can see the top. Basically, by using hydrogen or any other chemical-based source, we'll be able to store energy for a long time and a large energy quantity. And in the UK, government has published the hydrogen strategy to promote the development of hydrogen technologies. Globally, you'll see a lot of research activity. And a few weeks ago, UK government also passed the law. You will be able to see the government now is trying to promote the development of hydrogen infrastructure for future hydrogen systems. And then people may ask why we are still working on hydrogen engine. Obviously, when we burn the fossil fuel, the ICE, the combustion engine, will produce carbon emission. But when we use hydrogen or other zero carbon fuel, it will not produce any carbon emission. So if you look at this life cycle analysis of carbon emission, you'll be able to see, actually, if the engine burning zero carbon fuel, the CO2, the life cycle CO2 emission will be comparable to our fuel cell technology. Another advantage of ICE, hydrogen engine, is the cost. This is data published by AVL. The overall cost of a combustion engine, hydrogen combustion engine, in the middle bar, is only half of the fuel cell technology. So it does have an economic reason here. But hydrogen combustion engine is not new. You will be able to see the history of hydrogen combustion engine research. So you will see recently a lot of R&D activities in industry. And at Brunel, we have done some work on hydrogen combustion engine. That's a test cell. You'll be able to see the engine in the middle. And here I just show two results. One is CO2. You'll be able to see when we run hydrogen, there is no CO2 emissions. And if you look at the bottom graph, actually when we use additional air to dilute the combustion, we also now can mitigate the NOx emission. So there will be no any pollutant emission from the engine as well. This is another project. We convert a boat engine. Initially it's a diesel engine, but we convert it to be running hydrogen. Then similarly, we'll be able to see the blue line is a hydrogen result compared to other fuel will achieve zero CO2 emission. And for the NOx, again, when we use additional air, which means a higher lambda, we will achieve zero NOx emission. So it's a truly zero carbon and zero emission engine. And a few other projects we are working on. This is another very interesting engine concept. We call it opposed piston engine. We're trying to convert the engine to be a hydrogen, and we are going to use the engine on a ship, and we are going to do a demonstration, hopefully in 2025 in the sea. And another work is similar ideas. We want to convert the engine to be an electricity generator. So we are going to modify a two-stroke engine to be a very compact linear generator for different propulsion application. And another project is about ammonia. We collaborate with industry to add ammonia online cracker to convert ammonia to be a hydrogen ammonia mixture and then put it back to the engine. Then the engine will be a genset for the construction site electricity generation. And obviously we collaborate with the industry to work on the after-treatment system to remove the NOx emission. And also we do a lot of fundamental research, and you can see some optical engine, you can see some results, and also we do CFD simulations to assess the development of a hydrogen or ammonia engine. And another idea I would like to mention is dual fuel. Although it still uses diesel, but for the majority of the fuel will be zero carbon fuel. But the beauty of this engine would be we can still use existing diesel engine. We just slightly retrofit the engine, but we can significantly reduce carbon emission. You can see some results here. You can see roughly we can reduce about 25% if we use 20% hydrogen plus 80% methane. I think that's what I want to mention, a few conclusions. First, I think in the future, the propulsion system will be very diversified. There will be battery electric system, fuel cell system, or combustion engine. And I do believe hydrogen combustion engine is a very promising technology, will enable us to have a closer net zero target. I think that's all, and thank you again for your attention.
Thank you. Yeah. The next speaker is Jonathan May. He works in the GMS Energy as the principal, the manager. Yeah, his topic is high flex power project, demonstration of an industrial power to hydrogen to power advanced plants concept with up to 100% hydrogen in an SGT 400 gas turbine.
Thank you. It's been a real privilege this week to take part in the BrainLink event and to meet lots of new expert colleagues. So thank you for that. Particularly thank you to our two moderators and to Coast for the invitation to be part of this. The project I'm going to talk about, HyFlex Power, is a demonstration at a customer site in a real commercial environment of technology of burning in a gas turbine at up to 100% hydrogen fuel. The whole project is an integrated system coming from green electricity and water in, through an electrolyzer, compressed and stored on the site, and then reused as a fuel through the gas turbine and generating electricity again, doing the complete round trip. So here's a little more detail about the project. This is a European Union Horizon 2020 funded project, and Siemens Energy were part of a collaboration with a number of other companies and academic groups. In particular, Siemens Energy provided the gas turbine and the electrolyzer. Centrax provided the package for the gas turbine, and ENGIE, a French power company, operated the site and provided all of the integration aspects. The customer site that this is based at is a Smurfit Kappa paper mill in France. They are an existing commercial user with an existing SGT 400 12 megawatt machine running each year. The advantage of this site is that during the summer months they have a lesser need for power, and therefore we could bring technology in a demonstration unit gas turbine to trial and demonstrate the success for that. We've been running since 2020 and has culminated in testing in this summer 2023 of the unit running at up to 100% hydrogen. Here are the major components for the site that were installed for the project. Won't stay. There we go. Nearly. I'll give up. Starting from the top left, the deoxy unit associated with the electrolyzer. The electrolyzer that was installed on the site before 2022 operation. You can see the bottle bank of storage, which was a ton of storage. A ton of hydrogen on site allowed us to run for a couple of hours at high load, high hydrogen, but it did take a considerable time over a number of days to replenish that. So the test campaign was built around that cycle of testing and then replenishing the storage. A little bit of detail in some of the design changes that were used and the process that we went through to make this project work. To start with, we are designing, the new burner for the head end of the combustion system. This is based around pre-mixed jet burner technology with a centralized pilot and then an axial stage at the foot of the can. The can and transition duct gas path geometry are very close to the standard arrangements, and the flow then into standard combustion turbine section from the gas turbine. This was initially analyzed in a high number of CFD and heat transfer runs, now allowing us to optimize the design. The designs that were then selected that were suitable to be trialed, we produced through a metal additive manufacturing process, and these were large components that took up to 3 days to be manufactured at the Berlin Manufacturing Center. The additive manufacturing process created a good deal of opportunities to bring in the complex geometry that's necessary to accommodate the requirements of achieving a DLE combustion system for 100% hydrogen. But it's not only the challenge of meeting the 100% hydrogen. In the realistic application here, we envisage customers who will operate on 100% hydrogen, but also, when they need to, switch back to natural gas or any blend in between. So that's a huge technology challenge for the combustion system to be safe and reliable and have good experience operating at all of those blends between 0 and 100% hydrogen, whilst also having appropriate cooling features to have a good lifetime and control all of the usual aspects of a DLE combustion system. So over the project, we produced 26 iterations of this that were tested at our Siemens Energy high-pressure combustion facility just outside of Berlin. And over a period of a number of test campaigns, we did almost 50 days of testing on those in order to down-select and choose the hardware that we would take to the demonstration site, which was tested in the summer of 2023. Ahead of our testing in the commercial customer site, we also tested the unit in Lincoln in the factory on an extended works acceptance test. And this was only on natural gas, but it allowed us to optimize the control settings, allowed us to set up how we wanted the unit to run so that testing time at the site could be optimized and made as efficient as possible. Through the 2 summer testing campaigns at the sites, we were able to achieve the targets from the EU project. So we had double figures of hours of operation at greater than 80% hydrogen and several hours at 100% hydrogen as well. We are able, through this demonstration, to put into the real world and show entirely feasible to put this whole system integrated together so that it works and delivers that round trip using hydrogen as a storage medium to smooth the energy requirements. This is caused a lot of interest, and just as available are a list of some of the press releases that were made and the thanks that we need to offer to all the partners that were supporting this. This was covering a lot of companies and a lot of universities with many of the support and a huge amount of effort from those people. And where we get to from this is this was part of a Siemens Energy technology and R&D effort. And although this is demonstrated in SGT 400, which is at the smaller end of the Siemens Energy gas turbine product range, it was another one of the challenges that we set ourselves, was to make a technology that is not only suitable in that size, but that can be scaled. And we have the absolute intention and route map to deliver this same technology into a wide variety of products at very different power ranges in the Siemens gas turbine range. The importance for this is that it shows to customers who are buying an engine now, who may not have hydrogen available, that they have routes forward to bring this into any of their future products that they take. And because of the size of the existing fleets, with this retrofit option, then that allows a very significant contribution to in reduction of generation of carbon dioxide. Thank you very much for your attention.
Thank you. The final presenter is Professor Balachandran. He's a professor of the University College in London. Yes, his topic is hydrogen combustion technologies for decarbonized energy future. Thank you.
Thank you very much. I first of all thank COPST and the moderators, Professor Lee and Jin, for inviting me to take part in this exciting event. Today I'm going to talk about the pathway to hydrogen combustion technologies for decarbonized future. So far you heard quite a lot about what are the challenges regarding production and storage and utilization. I'm going to focus particularly on the challenges related to hydrogen combustion technologies. So we know that hydrogen is abundant in nature, and we also discussed hydrogen as a potential fuel. But if you look at the outlook, in short term, we need to focus on optimizing combustion technologies. And in long term, we should also look at hydrogen alternative fuels as well. But all of them at highest priority. So this is the IOP report, which I was one of the advisors, which advised the government and also the community in the UK. And this is what we see as a future for and place for hydrogen in power generation. So how that pathway would look like? If you look at immediate and short term, you'll evaluate the existing architectures for hydrogen readiness and also use hydrogen enrichment in existing gas turbine infrastructure. And the medium term, retrofit, and then also look at new architectures or reimagine new systems and also evaluate upstream and downstream impact. Finally, in long term, what you want to have is a decarbonized gas turbines and also how you would optimally integrate with the grid. So that will lead into a fully decarbonized energy future, while all other contributions from infrastructure development, transport, production, storage, digitalization, policy framework, and user experience feed parallelly into the same goal. Right? But what are the challenges? So let's look at the technical challenges of using hydrogen in a gas turbine. Right? So we know that hydrogen has high flame temperatures. And we also, in modern gas turbines, try to burn very lean, which means a flame blow-off is a problem. And particularly if you are going to use for aero engines, and flame blow-off is a serious issue. And combustion instability is a common problem that we will talk in a bit more detail. And flame flashback is a problem which emanates from the basic nature of hydrogen fuel. If you look at the graphs provided here, one on the right, you'll see ST over SL, which is a flame speed characteristics that comes because of the fuel nature. What it tells you is that how fast something burns or how reactive it is. Right? When in a turbulent environment, the x-axis shows how turbulent one can be. U dash is an indicator. The increase in turbulence, which is common in gas turbine situation, your flame speeds can go 200 times, which means existing infrastructure will be impossible to handle such a fuel. So we do evaluate different architecture. There are emerging technologies related to combustion architecture in pre-mixed, micro-mix, and lean direct injection, and common diffusion-based combustors generally can handle high hydrogen. But there are positive and negative for each of the different architectures, highlighted in the green there. One commonality is something called combustion dynamics, which is a problem that you design out at early stages. Otherwise, it will be a costly problem. Right? So what is a combustion dynamics? Right? The combustion dynamics is in ultra NOx technologies in gas turbine, comes from operating lean. You can see the two dots there. If you're operating on that zone, if there is any change in the x-axis, then you have a nonlinear change in the y-axis. Then it can go into a feedback loop that then you can have a damaged combustor. Right? So this is how a feedback loop looks like. Right? The inlet to the combustor, if there is any oscillation in the velocity or a mixture fraction, then what would happen is your flame area changes, and then you produce oscillations, and then it goes back into a loop and then keeps on growing. The time series shown in pressure can show that there is a stable operation, and then there is a growth and a saturation. Right? If that happens, and then if you have high amplitude saturation, then you end up having. So, and this is the multiscalar facility we have at UCL, which we employ to study this complex problem. Right? What you need to study is that we need to look at reactivity and reaction rate and pressure, temperature, etc., to fully understand this problem. So now, if we want to study the first part, immediate and short term, looking at hydrogen in an existing gas turbine, what we need to do, first of all, is to simulate in a laboratory scale the complex combustion behavior of a real gas turbine. So here the example is the SGT 100 or 400 fleets of Siemens Energy. And then what we have done is trying to mimic the combustion behavior in a laboratory scale. And also what we've also done is try to connect 2 or 3 cans together so that we can allow one can to interact with the other. So these are the existing gap in the research that is required to fully allow hydrogen combustion in the current gas turbine. And an example is that if you, in a single can, if you add just 10% of hydrogen, you can see at the bottom, the stability map drastically changes. The region of stability has reduced drastically just by 10% addition. So now let's move on to another new architecture, the LDI. So this is based on the originally published NASA architecture, where you have multiple injectors with individual flame elements all work together for producing the desired temperature and pressures for driving the turbines. Right? So what you can see is an airport supplied by 2 jet-in cross flows of hydrogen. So that, because of this complex interaction between these flames and the dynamics, right, understanding and using them to design the full system is quite complex. We need to understand the flame dynamics. So the next project, and we had presentation earlier about high flex power. Our role, UCL role, is to develop a generic H2 ready jet burner so that the flame is very similar to the original combustion configuration, and then so that we can study flow, the flame, as well as the static and dynamic stabilities. Finally, we cannot talk about hydrogen without talking about ammonia as a hydrogen vector. Right? So if you crack ammonia and to produce hydrogen, some element of ammonia is going to be there. That is something that can easily be used if you have a hydrogen combustor. So because our theme was looking at hydrogen for gas turbines, ammonia with hydrogen makes a very good candidate. So what are the challenges in this scenario? Ammonia is a new fuel, hydrogen is a new fuel, but combining together makes it even more complex. Ammonia has low flame speed, hydrogen has very high flame speeds. You could combine them together to get an optimum mixture. And at UCL, we study laminar fundamental studies, and then we extend it to turbulent flames, and then to fully practical combustion scenarios. And by doing so, what we believe is that by addressing all these important gaps allows us to help industry realize the dream of hydrogen gas turbines. Thank you very much.
Thank you. Thank you for the nice presentation of the all speakers. So let's do the 5-minute short break, and then we have another time to discuss about today's presentation.
Okay, good afternoon. My name is Hong Ho-jin. I'm from University of Lincoln, UK. I will moderate the second half of this event today. Okay, so this is now the panel discussion time, so you can ask the many questions if you can ask this question if you have. So, do you have any question or any comment regarding this previous presentation? Do you have? Okay, then let me ask first to the panels. I think, first of all, what kind of the technical challenge or barrier regarding feasible hydrogen ammonia storage, production, and utilization include the combustion, do you think? So probably I think Professor Che first regarding
Yeah, I think
hydrogen.
that's $1 million question, but let me first think about why we are looking for different energy carrier, not fuel based on coal or not petroleum. Why we are thinking about different types of energy carrier, because we're looking for a more sustainable society. Then this is not free lunch. So whenever we're looking for sustainable society, we give up the most cost-effective way, and we are investing money or our resources for more sustainable resources, which is maybe potentially hydrogen. So I think the biggest challenge we are facing always is cost. We have a material scientists working hard, process engineers, they develop optimized processes, but still the production cost of ammonia hydrogen is very high. And also we don't have infrastructure. So for example, we have infrastructure for ammonia, but still we don't have enough infrastructure for hydrogen. So by shifting our infrastructure from coal or carbon-based energy source to hydrogen is another industrial evolution, I think. So we are not ready yet, but I think we are working hard. So that's, I think, the most challenging things we are facing. Maybe some other people, some other panel add on that, but that's my personal view. Thank you.
If you're looking at ammonia and hydrogen technologies, depending on a country's infrastructure, there could be challenges. For example, if infrastructure for fertilizer use through ammonia already exists, ammonia mobility is relatively easy. Whereas hydrogen is kind of a new fuel for large-scale use. So most of the infrastructure related to mobility of hydrogen is a challenge for many countries. And if you consider production, for example, again, production through conventional method, both hydrogen route to ammonia is quite common. However, if you are looking at green hydrogen, green ammonia, then there is a serious problem because, first of all, if you are going to use electrolyzer manufacturing is not on a mass scale, so which means that it is a bit slow. Even getting hold of electrolyzer is currently difficult. So improving and optimizing manufacturing of electrolyzer is a serious challenge that has to be addressed before a supply problem can be addressed.
I think from a end use, two really nice answers, by the way. I think from an end use, the technical challenges are all well within the society's capability of meeting. Where we have some short-term challenges, it's because what we're doing is we're comparing technologies that are decades old and have layers and layers of development built one after the other. And now we are faced with a situation where there's an explosion of variety. Each of those are items that we have experts around us in conferences such as this, where we meet people who are tackling those challenges all day, every day. What we need to do is meet those challenges one at a time, produce usable products that will fit with the overall infrastructure and the production so that it comes together at the same time, and then prioritize how we choose which of those to do. So I think all of those technical challenges are very much in our capability, and it is a matter of picking good ones to pick first so that we can make good progress towards a sustainable future and building on those successes.
maybe let me add a bit on. Yeah. So let me talk about from the perspective of biochemical engineer, because I'm from bio background. So what I feel that actually the bigger challenge from bioprocess actually is the type of the material that you use. I believe because I work on microalgae, so the type of microalgae that you use, let's say the strength of material, the strength of this microalgae is very important, because this will identify the amount, the efficiency of the biohydrogen, bioethanol that you produce. So I believe the type of the material that you use is very challenging nowadays. That's why we have a missions, right? Currently, I'm setting out a new consortium. We call it Algae Biotech Consortium. So in this consortium, we are collecting, I think, more than 100 of type of microalgae. So we hope that using this consortium, we can combining all the effort from the scientists, from the engineers, so that we can have something, we call it seed bank, right? Seed bank, so that we produce as much biohydrogens in this area. So this is, I think, it's possible to work, but with the help of everyone. Thank you.
Maybe I can add a few words. I think the challenges for combustion engines, I think I will summarize into three. The first will be infrastructure, because I think that's quite important, as mentioned by other panelists. And the second one will be the cost of the fuel. If you use hydrogen or ammonia, they are new things to the society. And obviously, currently, I think the cost of these fuel will be a key element for the wide application. And thirdly, the engine technology itself. I think the most important one is the durability. Obviously, hydrogen has some special, properties, is some embrittlement, and also for ammonia, obviously it's a corrosive gas. So I think there are a lot of work need to be done on these durability experiments. I think that's all I want to share. Yeah.
Let me touch on the hydrogen production and the transport side. So the UK government recently announced the UK CCUS clusters. So there are two UK CCUS clusters in the UK. One is the HyNet and the other is the East Coast clusters. And to implement this decarbonization in industry, they also announced the specific project to implement these clusters, and which include the green hydrogen and blue hydrogen. So I think it's very important to cover the both aspect of the hydrogen production, so green and blue. So there's the good balance between the two is important. And for the hydrogen transport, I think the cost-effective way of the transporting the hydrogen is important. So we have to find a way. And one of the projects I was involved in the transport the hydrogen using the existing natural gas pipeline. So once the hydrogen is produced, then we can mix the hydrogen with natural gas, and then we can transport the gas mixture of the hydrogen and natural gas through existing the natural gas pipeline. And then once we transport the gas mixture, we can separate the hydrogen from natural gas using the separation process. So we are trying to find the cost-effective way of the hydrogen production and the transport.
Okay, thank you. Do you have any comments or question? Yep.
So my question is from Professor Soryong. Since you presented some of the ammonia utilization work, and particularly emphasized on the utilization of ammonia and the thermocatalytic decomposition of ammonia. So, being a budding researcher in heterogeneous catalysis, I understood that ruthenium is the most explored catalyst for this particular process. So if we say that on the scale of 1 to 10, so where you can identify the whole process of thermocatalytic decomposition of ammonia particularly for the hydrogen production. And since it is cost effectivity is a major challenge, so can you suggest something for the non-noble metal catalyst regarding this? Thank you.
Right, thank you. I think that's a great question. So, what I think, this is my personal view, but all these lithium-based catalysts, they add some other, hybrid type, and they're trying to, minimize that, energy input to increase temperature and to control the pressure. But still, I believe, people looking for different, material, but always the stability or lifetime, they concern. Or even you change the material from the proven one to the new one, if you fail your system, you may go back to the initial material, even if no matter of cost, it's the matter of success or fail. So I believe, a lot of scientists, catalyst, which is good, topic, and also still ongoing effort is tremendous. So, but however, I don't know whether there is any alternative at the moment, but people, trying to increase the efficiency by combining with the other, inorganic forms, and they trying to increase that efficiency, conversion efficiency, and also reduce the operating cost. But still, I believe, we are just, some step, but still we need to get more steps, to design new catalyst, replace that lithium-based one. I think we are on the way. Yeah. Thank you.
Any other comments or questions?
Thank you. Thank you for the presenters so far. Yeah, we've learned over the time that, we made to know today that hydrogen is a zero-emission fuel, and the reason why many conferences, even the COP28, is to mitigate the presence of CO2 and to alleviate the climate condition. And over the time, we've learned, it was also mentioned today that hydrogen system is very expensive. That has been the challenge. So I want to ask the panel, how would you go about designing efficient and cost-effective hydrogen production system so that the issue of CO2 or whatsoever challenges that the climate is facing presently will be mitigated? Thank you.
So before if we don't have to capture CO2, so we don't have to produce blue hydrogen, so we don't have to care about the carbon capture or decarbonization, then the hydrogen production plant is based on the steam methane reforming. So 99% of the hydrogen production facilities based on the SMR. And if we want to capture CO2 from the existing SMR plant, there are several candidate streams where we can capture CO2, but the most advantageous stream where we can capture CO2 more economically is the syngas stream, because it's high pressure. But even though we capture CO2 from that syngas streams, the maximum achievable carbon capture rate is limited to 60%. For that reason, if we want to capture CO2 from a hydrogen plant, we have to use different type of the technology rather than the SMR, which is autothermal reforming technology. If you use the autothermal reforming technology and we apply the carbon capture process to the high pressure syngas, then we can achieve 90% carbon capture rate. For that reason, I think most of the project to build the blue hydrogen process is based on the autothermal reforming rather than steam methane reforming. So that in that way, we can increase the carbon capture rate. Also, we can reduce the production cost of the hydrogen.
I will take a slightly different approach. if you look at the hydrogen production, why people are fascinated about green hydrogen, for example, right? So if you don't want to go into carbon capture in any process, then the electrolysis route is a nicer route. However, you have a problem. If you don't have existing infrastructure for solar and wind, then that is not a reality for many countries. Right? So if you look at, for example, I will give an example. India, for example, has 30 to 40% of wind and solar utilization in southern part of India, where the grid capacity is already maximum. So if they want to increase their solar utilization, only way is do something else like hydrogen. For some of those situations, the hydrogen becomes much more attractive. So what you will see is that many countries would become green hydrogen producing countries. Many countries would become green hydrogen utilizing countries, right? So the focus then would be on cost efficiency of the technologies. So solar is getting cheaper and cheaper, right? Then the thermodynamic efficiency would become irrelevant, right? The same thing would extend to other storage and other technologies as well. So this is a different approach, particularly focusing on green hydrogen space.
Any other comments?
Yeah, maybe let me add a bit for just now discussions, right? So basically, what we are doing here, actually, we produce biohydrogen as well. So I believe, as I mentioned in my previous presentations, that microalgae can very good solution for carbon capture. At the same time, you can produce biohydrogens. So I think this is one of the solutions that I think possible to solve the problem, because I believe you mentioned just now the COP28 now, they are talking about climate change, carbon dioxide. All this actually is linked to this carbon credit, right? So I believe microalgae should be one of the solutions here, because microalgae have a lot of functions. One of the functions is carbon captures, another is a future food biofuel. So basically I can say this is one of the ways that we can solve, but I believe there's a long way to go because still undergo R&D process. I believe maybe we need everyone help to make this one of the history. Right? Thank you so much.
Thank you. Do you have any other question or comments? Right, then as we know through this presentation and other reference, the hydrogen has the broad range of flammabilities, and ammonia is also toxic and corrosive. So let me ask, what kind of the safety concern with the using hydrogen ammonia we face?
Yeah, maybe I can start. Right. So as you know, when we use a battery for EV electric vehicle, we concern about the safety. Maybe battery itself compromised, and we have a fire. It's not easy to eliminate that fire using current method. And hydrogen also is a flammable gas, right? And also ammonia is toxic. I believe technology is there to control their safety or guarantee their safety. But always, I believe we are doing some, multi-barrier approach. If we fail this one, maybe, end user or manufacturer, they add another barrier to make sure this is safe for our daily life. I think that's a minimum guarantee for everyone, right? So, a lot of chemicals, basically, in my opinion, anything synthetic. This is not environmental friendly, and also there is a risk. So the way how we can control or mitigate or manage that risk, this is the job of scientists and engineers. So I think technology are there, technology is there. But by recognizing potential risk, then we can end up some potential solution. I think that's the good approach, rather than just concerning about the safety. Right. Thank you.
Thank you. John?
I think I share the same view as the professor. Sure. I think obviously when new things come out, there will be new concern about the safety and the risk. And but I do believe it's my personal view. Once we have really looked at these issues, it will always be a solution there. But obviously, initially, we need to look at the potential, at least, for example, reducing CO2 or reducing other pollutant emissions. If there is a good opportunity in terms of efficiency, in terms of these CO2 emissions and pollutant emission, there will be more research activities around the safety aspect. For example, here, obviously in our research lab, we need to address these safety issues when we run our engine testing. And I think we control it very well. Obviously, we need to follow the very strict risk assessment. And once we meet that risk assessment and we develop our mitigation measures, running hydrogen engine is okay. So for the application side, I think it is similar. Once we have phase into the application side, there will be more resources, more effort in mitigating these risks. I think there shouldn't be a problem, as mentioned by Professor. Solutions are there, technologies are there. It's just a matter of the time. Yeah. Thank you.
Thank you. John?
Thank you. Yes. So, I mean, absolutely clear that safety can't be something that you tag on at the end. It has to be something that's part of the design process and the development of the technology. I think real-world experience helps and develops that understanding. You have to try things out to learn some of these lessons, and you have to apply them in conditions that are realistic and meaningful, so that that can be used to develop solutions that will become standard. How we work to, I think, is a really important that industry and academia come together to look at. So a lot of the protections that are in place for use of the existing fuels, fossil fuels, are based on a lot of experience and are consistent with the properties and the use of those fossil fuels. It is a mistake to assume that the mitigations that are in place can be transferred immediately over to new fuels. Hydrogen and ammonia are very different. They've got different risks and they've got different properties. So in the production of units for use with hydrogen, whether that's in production or in end use or storage and transportation, it has to be designed in from the beginning. We have to develop across industry new standards that are applicable for hydrogen, so that production, whether that's a testing criteria or a safe operational criteria that you might have for unburned fuel in a hydrogen use, they all have to be reconsidered to match the hydrogen properties. But I think it's clear that a solution that is not fulfilling safety requirements is not a solution.
Excellent point from all the panelists. Right? I want to add a little bit more details, because we are at a complex situation where we want to evaluate two completely different fuels for varied application, not one application. We want to do it decarbonization for all sectors. Right? So what it means is that, one, creating necessary equipment and infrastructure that allows safety. For example, at the moment, quite a lot of the equipment intended to use in general systems, like John was saying, cannot be used directly in hydrogen and ammonia situation. And there is no particular testing associated with use of hydrogen and ammonia for some of the instruments that are available. So that might give you a false confidence if you use the wrong instrument for safety and it is not tuned to the right fuels. One is creating capabilities for sensing and controlling the situations. The second is creating the workforce and the people who can create systems that are, one, safe, and then safely used for the use as well. Then you go into policy situation where you create new policy or policy additions that cover new use, for example, right? So I'll give you an example. So we were evaluating policy matters on farm vehicles, which uses conventional fuel. But if you look at a gap, for example, JCB, when they wanted to do a farm vehicle with IC engines, there is no regulation that covered vehicles moving below 20 meter per second on a motorway, right? So that was a policy gap the technocrats has to work closely with, right? That is a safety matter. Then if you look at that as a whole system approach, engineers wonderfully design, for example, Siemens Energy will design a wonderfully superb hydrogen engine for intended use, right? Sometimes you create systems for intended use, but the users sometimes use it for unintended way, right? So that can create a new issue, right? So to understand this, we need to work closely, like it was said, users and researchers and other stakeholders, industry, manufacturers, and other participating industry has to work together to come up with identifying new avenues for creating a safe hydrogen and ammonia use.
Thank you so much. Right. Do you have any comment or any question regarding safety aspect of hydrogen and ammonias? Okay. My final, because now time is limited, so final question is, we usually talk about the hydrogen and ammonia utilization in terms of power generation and transportation. Is there any potential application of these hydrogen ammonia rather than just power generation or mobilities, do you think? For example, can we use ammonia as in a kitchen, do you think?
One obvious evidence, once you have ammonia, it's a kind of feedstock for many other chemical fabrications. So, not just hydrogen, it can go some chemical, it can go, fertilizer, it can go different ways. So, yeah, that's a good point. The production of ammonia, it will be transformative, producing other final product, and not just we are looking for, energy source, but also it can be other feedstock fabricating or synthesizing different chemicals. So I believe there are a lot of approaches using ammonia as an intermediate or feedstock to produce chemicals, fertilizer, other things. Yeah, that's only what I know. Yeah.
So if you look at industrial process, quite a lot of the industrial process already incorporate low calorific fuels, right? So in those situations, ammonia is quite good candidate. And hydrogen is a very good candidate for domestic use, right? So I could see possibility of having hydrogen cooperative where small remote regions are fully powered locally, decentralized energy distribution. Hydrogen could be a very good vehicle, right, for domestic use as well as for farm use, those kind of or heating, etc. Right? That is a good case for that.
Thank you. Professor,
I think I can think of two examples to make use of the ammonia. One of the option is to produce urea by reacting the ammonia with CO2. Then you can produce the fertilizer like a urea. And the other option is we can use the ammonia as a fuel for ships. So most of the shipbuilders consider the ammonia as an alternative fuel, clean fuel instead of the diesel or natural gas. So by burning the ammonia, and then we can use the ammonia as a fuel. Also, obviously, the ammonia is very toxic. So as a fuel, ammonia has to compete with the other alternative fuels like methanol and the synthetic fuels. So there is also challenge there, but I think ammonia is very promising alternative fuel at the moment.
Let me add a bit. Okay. So basically, I can say, yes, direct answer to a question. I think ammonia have a lot of applications. Not only I mentioned, like you mentioned in transportations. I believe in ammonia, as Professor Ang mentioned also, ammonia also can use as fertilizer, because I have one project working on this fertilizer productions from food waste. So as you know, food waste, they produce a lot of ammonium. So we can convert the food waste become ammonium fertilizer. We call it compost. So within 24 hours, put it in the machine, so you become a compost. So this compost not only for fertilizer, we can use it as a combustion material as well. I think this is one of the good example we are working in that directions. And also talking about hydrogens, I believe in this area, I believe hydrogen not only for transportation, I think you can use a lot of applications in let's say medical device, used for other consumable chemicals. I think this is some of the applications. Just think that not only because everyone talking about ammonium is very toxic, not good, but I think this depends how you use it. All right, I believe a lot of medicine, if you use it the correct way, then you use it the right way, then you will have some positive effect. If you use it the wrong way, definitely negative effect. So it depends how we use it, I believe. This is my opinion. Thank you so much.
Thank you. Any comments? Okay. Let me conclude. We have great times to share our knowledge, insights, and we have also great network opportunity. I believe that although this event is now end, it's not end of our work. I think this is the begin to start of tackling the global problem we face now. So, and also I would like to I hope to this event will continue to have a more a good potential collaboration between Korea with other country. So thank you so much again to joining this great BrainLink X-Lab Day event. So I believe you are all enjoy this today's session. Okay, thank you.